Hi there, this is Heath. We're starting day 3. What we're going to do today is we're going to finish up the Affine Cipher, which we started talking about last time. And then we're going to start 2 new ciphers, the Vigenere and Playfair ciphers. So let's get started. One of the things we talked about last time was Theorem 2.1 that said this congruence has a unique solution if and only if GCD of A and N is equal to 1. And I skipped the proof last time because we were running short on time. But we have time today to get through the proof. So let's look at the proof. What we're going to do is we're going to assume that AX is congruent to B mod N has a unique solution. Well, that means that AX is congruent to 1 mod N has a unique solution. Because this is just a special case where I'm assigning B equal to 1. If all of these have a unique solution, then this is just a special case. Oh, okay. Well, then, in order to be congruent to 1 mod N, well, that means there is some solution P such that A times P may not equal 1, but it equals 1 plus an exact multiple of N, plus N times Q. That in order to be congruent to 1 mod N, it could be 1, or it could be 1 plus N, or it could be 1 plus 2N, or 1 plus 3N. But it's some number that reduces down to 1. So what I'm going to do with this equation here is bring everything except for the 1 to the one side. Therefore, AP minus NQ is equal to 1. This is important, and we'll show why in a second. We're going to let D equal the GCD of A and N. Then D divides A, so D divides AP. Also, D divides N, so D divides NQ. But since D divides AP and NQ, then D has to divide AP minus NQ. But that means D divides 1. But D is a GCD, which means it's a positive integer. And the only positive integer that divides 1 is 1. Where'd my pen go? Here it is. The only positive integer that divides 1 is 1. And so D is equal to 1. And that proves the second part, that the GCD of A and N is equal to 1. And so we have a proof in this direction that if the congruence has a unique solution, then the GCD is equal to 1. But this is an if and only if statement, so we have to prove the other direction as well. But the other direction we did last time. Assume that the GCD of A and N is equal to 1. Then we could just use the extended Euclidean algorithm and solve this congruence. Then the extended Euclidean algorithm gives a unique solution to any congruence. That direction's easy. It's the other direction that's a little hard. Okay? All right, so let's move on. So far, we've covered these three character-based crypto systems. I say character-based because we're encoding just one letter at a time. We're going to look at a weakness that's common to all three of these ciphers. And then we're going to look at a character-based crypto system that doesn't have that same weakness. Okay? So, as many of y'all mentioned on the discussion board, character-based crypto systems can be vulnerable to a form of attack that we haven't directly covered, the frequency-based attack. The distribution of letters in English is not even. In fact, it's highly uneven. There are a lot of E's, there are not a lot of J's and Q's and Z's. And that unevenness can assist us in identifying the plain characters that correspond to frequently used letters in a message. I have posted a list of letter frequencies on the homepage. You may want to use that for some of the problems on the next homework assignment. Okay? So frequency-based attacks is one attack that we can use. We have a second attack that we can use for the Affine Cipher. All three of the crypto systems we've seen are vulnerable to frequency attacks, but the Affine Cipher has a special weakness, which we illustrate here. I have this message, and it was encrypted using an Affine Cipher. And just to remind you, for an Affine Cipher, we have to choose A and B, with A has to be relatively prime to 26, and then the encryption is AX plus B, and the decryption is the inverse of A times X minus B. Now, if I look at the frequently used letters in this ciphertext, I find that T gets used 8 times, F gets used 7 times, G and J and M each get used 5 times, and then every other letter is a little bit less frequent than that. And so we're trying to crack the Affine Cipher. We're playing Oscar's role. We do not know the key, but we do know these letter frequencies. And so we might guess that T represents E and F represents T, the two most common letters in the message represent E and T, which are the two most commonly used letters in English. We guess that, but we can prove that that doesn't work. We can disprove this hypothesis without having to keep guessing other letters. If E has a value of 5, and it gets represented by T, which has a value of 20, then A times 5 plus B is congruent to 20. And if T is represented by F, then A times 20 plus B has to be congruent to 6. So I have this congruence, and I have this congruence. If I subtract them, I get this congruence. A times 15 is congruent to 12. When I subtract, the B's go away. And now I just have a congruence with one variable in it. Negative 14 and 12 are the same. We're just adding 26 here to get this to be in the range from 0 to 25. But this is a congruence we can solve. The multiplicative inverse of 15 is 7. We multiply both sides by 7, and then we get 105A is congruent to 84. But 105 reduces to 1, and 84 reduces to 6. So we get A is congruent to 6. And now we've solved for A, but this A is not relatively prime to 26 because 6 and 26 are both even. And therefore, A equals 6 is an impossibility. And so our conjecture that one of the letters is wrong, our conjecture about the letters has to be wrong. It cannot be the case that E encodes to T and T encodes to F. So we go back to these letter frequencies again. We know it's not the case that this letter is E and this letter is T. So let's stick with the hypothesis that this is E and try maybe that this is T. And if we try that, we're going to find that the calculations don't work again. Let me show you what happens over here in the margin. If E goes to T, so E equals 5 goes to T equals 20. That means A times 5 plus B is congruent to 20. And if T goes to G, T is 20 goes to G is 7, then A times 20 plus B is congruent to 7. If I subtract 2 minus 1, I get 20A minus 5A is 15A. B minus B goes away and gets me 0. And 7 minus 20 is negative 13. But negative 13 is the same as positive 13 because we're in mod 26. If I add 26, that gets me into the range from 0 to 25. To cancel the 15, I need to multiply by 7. 7 times 15A is congruent to 7 times 13. Or 105A is congruent to 91. 105A is congruent to just A if I take out 26s. 91, if I take out a bunch of 26s, leaves me with 13. And 13 is not relatively prime to 26. 13 is not relatively prime to 26. And therefore, this doesn't work either. And in fact, if we try T goes here, that doesn't work either. But if T goes here, we can solve this pair of congruences. And we get a value for A that is relatively prime to 26. Excuse me. And now that we know what A is, we can go back and substitute and solve for B. I'm substituting A into this congruence right here. 3 times 5 plus B is congruent to 20. And so B has to be 5. And so just guessing where the E and the T were, we found a pair that lets us to solve for the congruence. And now we know how to solve this entire cipher because we first subtract B equals 5, and then we multiply by the inverse of A equals 3. A inverse is 9. And so we take 9 times A minus 5. This is a decryption operation here. And so the first two letters of the message become A and L. I'm not going to take the time to decode the rest of the message. This is what the plaintext is. Algorithms are quite general definitions of arithmetic processes. That would have been a hard thing to just guess by substitution. But once we figured out where the E and the T had to go, we could solve the congruence and get all of the other letters immediately. Okay? All right, so let's look at the Vigenere cipher. The Vigenere cipher is an alphabetic cipher that doesn't have the weakness of being able to be solved with frequency analysis, and I'll talk about why in a moment. It's named the Vigenere cipher, but that's a historical mistake. It was actually described by Giovanni Battista, but historians didn't know that. They described it as the work of a later mathematician. And so Vigenere got credit for this cipher, but he wasn't one who discovered it. So, It's a variation of the shift cipher, but it was so hard to break that it took over 300 years to break it. It was discovered in 1553. It was not broken until 1863 by Friedrich Kasiski. So what we'll look at today is how the cipher works, and then we'll talk about how Kasiski broke the cipher next time. And so this was considered to be an incredibly secure cipher for over 300 years. And historically, that makes this very important as a cipher, but it has been broken. So Alice wants to send this message. Cannot meet tonight, will reschedule next month, using the Vigenere Cipher. She and Bob have agreed upon a code word, and a code word they have chosen is hokey. And they're going to use this this code word to encrypt the message. So what Alice does is she converts her message into numbers. C becomes 3, A becomes 1, N becomes 14, so on and so forth. And underneath each letter, she writes the code word over and over and over again. H-O-K-I-E, 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 so on and so forth. If you run out of letters at the end, the last repetition of the code word may be incomplete. That's okay. But you keep repeating the code word until you reach the end of the message, and if it ends in the middle of a code word, that's okay. And what we're going to do now, what Alice does, is she adds these numbers together. 3 plus 8 is 11. 1 plus 15 is 16. 14 plus 11 is 25. I'm going to move on to the next slide here. 11, 16, 25, so on and so forth. And that's the ciphertext. Okay? Why doesn't frequency analysis work? One reason is that 2 input letters, N is a frequently used letter, but sometimes it encodes as a Y, and sometimes it encodes as a W. And so the frequency of the N is distributed among multiple possibilities. And it works the other way around. The output values, B might show up frequently in the outputs. In fact, it looks like it does. I see about 4 of them already. But sometimes B was a T, and sometimes B was an M. That is, just because a letter is frequently used in the output, I can't match it to E. I can't match it to a common letter because it might match up to multiple input letters. This is not a one-to-one mapping of letters to letters. And so we can't use frequency analysis on this cipher. So the same input letter can have different output values. The N's at top were encoded as a Y and a W. And the output values can correspond to 2 different inputs. B corresponded to both T and M. This is what we call a polyalphabetic crypto system. The method of encryption is still character-based, one base character at a time. So it's alphabetic, but a plain text character can encode in multiple ways. That makes it polyalphabetic. The same letter doesn't always encode the same way. So this is our first polyalphabetic crypto system. Let's look at another crypto system. This is a system called a block cipher. It's also resistant to frequency-based attacks. And what we're going to do in this cipher is encode pairs of letters instead of single letters. Okay? So Alice and Bob have agreed upon a 25-letter string in which no letter is repeated. Now that means that one letter of the alphabet has to be omitted. And historically it was usually J, but you could agree to limit Q's in the message, for example, instead. It just means if there's a J in the message, we're going to drop it and assume that the other person is intelligent enough to put the J's back in where they need to. All right. Alice and Bob stored this 25-letter string in a 5x5 array, and that serves as the decryption and the encryption key. So this is the key we're using for this example. Alice wants to send the message urgent matter. She begins this by breaking up into 2-letter groups, URGENTMA. If I see a double letter, I have to separate the double letter. I can't have the same letter show up twice in our bigram. And so I'm just sticking an X in there just to separate out the 2 T's. No bigram may contain a repeated letter. Doesn't have to be an X, just has to be something that Bob will recognize as being an extra letter here. Okay? Then TE, and then an R, and then I had a space left over after the R. So I also have to insert an X at the end of the message to have an even number of letters to encrypt. Okay? Again, you do not have to use X. You can use any agreed upon insertion, but X is perfectly fine here. So those are the 2 requirements that Alice has to have in her message. No repeated letters inside a bigram. And if we end up with a single letter left over, we have to pad that at the end to get a bigram at the end. Okay? So here's how we're going to encode this message. I look for each bigram in the message. The bigrams were URGENTMA TXTE and RX. I find the bigram in the message. It was U and R, and they're on this diagonal of a rectangle. And what I'm going to do is I'm going to reverse the diagonal vertically. The diagonal is also pointing downwards. The U is on top, the R is on bottom. So then I'm going to flip the diagonal left to right and replace UR with NG. So since the U is on top, the N is on top, the N will still come first. Okay, so we're just flipping the arrow across a vertical axis here. Okay. Let's try the next one. The next pair was GE, and GE are down here. They form this rectangle. I'm going to reverse that arrow. Since G is down on the bottom row, then I'm going to put the M first and the EW second. So UR became NG, and then GE became MW. Okay. We have a special case, and that's what if these two, the letters in the bigram don't appear in different, don't generate a rectangle. They all lie on the same line or the same column. So if both letters are in the same row or the same column, then what we do is we just advance each letter along that row. So we have encoded UR and GE, and they became NG and MW. NT is on the same row. And so the N advances forward, which wraps around to U. And the T advances forward, which doesn't wrap, it just advances forward to S. Okay. The next bigram was MA, and MA is in the same row. So the M advances forward and becomes A, and the A advances forward and becomes R. Okay. Alice's message doesn't have any bigrams that show up in the same column, but if they did, like NI, we would do the same thing. The N would advance to a Y, the I would advance to an R. So NI is not needed for this message. I just wanted to show you an example of one that's in a column. Okay? So if we do the full ciphertext of the message, we get NG, MW, US, AR, SQ, SK, and MY. Okay. What kind of vulnerabilities are there in the Playfair cipher that Oscar might exploit? We'll talk about that for just a second. The one of the problems is that we can't. It's not monoalphabetic. That is, a T can encode in different places depending on what other letter is in its bigram. If T is in the same row with its partner, then it advances to an S. But if it's in the same column with its partner, it goes down to a Q. And if it's in neither the same row or the same column as its partner, then it flips across a diagonal and shows up somewhere else in the matrix. And so if somebody did not have access to the key, Oscar is receiving the message, is observing the message, and wants to break the code but doesn't know this pattern. Is there some vulnerability that Oscar might be able to exploit? Be thinking about that. We will look at that later on this week. All right. Y'all have a great day. Take care.